When you tune a control system, you check and adjust the instruments in the system to ensure that it operates within specified limits. The procedure is a lot like tuning an automobile engine. No two engines are exactly the same, but if you know the engine and you use a logical tuning method, you can probably do the job. Now, in a plant, no two process control systems are exactly the same. But with the right knowledge and resources, you can tune a variety of control systems. What we'll do in this program is look at some of the basic principles of tuning a pneumatic control system. Then we'll look at the process characteristics that are important in tuning, and we'll examine some common tuning methods. Afterwards, we'll see how an instrument technician tunes a control system. Most of the information that you'll learn from this program can be applied to the pneumatic control systems in your plant. Okay, now let's see what tuning actually is, what part of a system is tuned, when it's tuned, in general, how it's tuned, and let's look at some information sources that you should know about. Generally, the act of tuning involves checking and adjusting instruments in a control system. But more specifically, when you hear someone talking about tuning a pneumatic control system, they're usually talking about adjusting a controller. The function of a process control system is to maintain a process variable at or near a specified value called set point. Actually, if nothing in a process ever changed, we wouldn't need a control system. But because processes do change, a control system is needed to sense the change and return the process to set point within a minimum period of time. When you tune a control system, the specific adjustments you'll make depend on the type of controller and the process being controlled. For example, this PI controller provides both proportional and integral action. When tuning it, you have to make at least two separate adjustments. A gain adjustment to set the proportional response of the controller, and a reset adjustment to set the controller's integral response. Controllers are tuned for specific reasons. You might have to tune a system in your plant after new equipment has been installed. Maybe you'd tune the control system after you've repaired equipment in the system. Sometimes you tune a controller to compensate for a minor system-related problem that affects control, but can't be corrected immediately. Now, when you're asked to tune a system, you don't just walk up to the controller and start making adjustments. The first thing you do is to learn all you can about the system. There are several different sources of information that you'll find useful. One useful information source is other people who know the system. These people are control room operators and many of the experienced instrument technicians that you work with. Another excellent source of information is a document called a Piping and Instrumentation Diagram, or P&ID. It's a diagram of a process or several related processes, and it's composed of symbols that identify the process components and interconnected piping. Let's look at a simplified illustration of what you can learn from the P&ID. In this cooling water system, water is pumped through piping to various pieces of equipment in the plant. The water collects heat from the equipment and carries it off to a heat exchanger. There, the heat is transferred from the cooling water to raw water. Raw water is simply water taken from a river or similar source. After exchanging its heat, the cooling water is pumped back to the equipment. The raw water is pumped through the heat exchanger to a cooling tower where it is cooled. After cooling, it is pumped back to the heat exchanger to repeat its cycle. The system uses a basic feedback control loop to control the temperature of the cooling water. It works by controlling the flow of raw water. If the flow is increased, the temperature of the cooling water will decrease. Conversely, the temperature of the cooling water will increase when the flow of the raw water is decreased. Let's add the control loop to our simplified illustration of the process. A temperature sensing bulb is used as the primary element in the control loop. It converts the temperature of the cooling water to a gas pressure, which the system's transmitter converts to a pneumatic signal. The control loop also contains a recorder. The recorder documents the value of the cooling water temperature. There's also an alarm similar to this one in the control loop. The alarm indicates a high cooling water temperature. The system's controller is a typical pneumatic proportional plus integral, or PI controller. There's also a hand station in the control loop. It provides for the selection of manual or automatic control. The final control element is an actuator valve assembly that controls the flow of raw water to the heat exchanger. So by studying the P&ID, we've been able to learn about the cooling water system and its control loop. Another source of information that you'll find very useful is a control logic diagram. The diagrams are sometimes called loop sheets or just loop diagrams. A control logic diagram is a diagram of the instruments in a specific control loop. Now, you can use this diagram of the cooling water system to learn that the temperature transmitter's range is 0 to 200 degrees Fahrenheit. The diagram also shows that set point in this system is 85 degrees Fahrenheit. The controller settings are also on the diagram. The controller is adjusted for a proportional band of 100%, or a gain of 1, and a reset time of 1 repeat per minute. In addition, the diagram has specific calibration settings that are used in the initial calibration and setup of the instrument. The control valve is the last element in the diagram. It is closed with a 3 psi signal from the controller, and it's open when the signal from the controller is 15 psi. In addition to this information, you'd also learn how the equipment is connected in the control loop. So, a control logic diagram contains a lot of information about a specific control loop. You'll find them very useful. There's one other document that you'll probably use when you tune a controller. It's an instrument calibration record, or instrument history record as it's sometimes called. The calibration record identifies calibration settings for specific instruments. For example, here are the calibration settings for the cooling water temperature controller. And this is the general information that was entered by the last technician to calibrate the controller. This general information tells you how the technician calibrated the controller. So you can see that by studying the P&IDs, control logic diagrams, calibration records, and talking to operators and other technicians, you can learn a great deal about a system. But when you want to learn how adjustments are made on specific instruments, you would refer to the instrument manufacturer's service manuals. Now, after you have thoroughly studied all the documents that we've mentioned, you might think that you'd be ready to go out and tune a system. But you should also be aware that there are process characteristics in the system that impact on its response to a disturbance. We'll discuss these characteristics in the next part of the program. Before we do that, review the material in your text. Make sure that you understand what tuning is, what is involved, and when it's done. Also, check your knowledge of information sources that are used by instrument technicians when they tune control loops. Ask your instructor to explain anything that you don't understand. Process control systems have specific characteristics that affect the way they react to disturbances. The three most important of these are resistance, capacitance, and dead time. You'll need to know about these characteristics when you tune control systems. So, in this part of the program, we'll look at some of the characteristics of the cooling water system that we discussed earlier. What we learn about this system can be applied to most systems. Here's a simplified illustration of the system's heat exchanger. In the illustration, the heat exchanger walls have been removed to show the internal tubing. This gauge indicates the temperature of the raw water leaving the heat exchanger. And this gauge indicates the temperature of the cooling water leaving the heat exchanger. After the cooling water has collected heat from various pieces of equipment in the plant, it flows through the heat exchanger tubing. Raw water flows around the tubing. Heat is transferred from the cooling water to the raw water. Now, if we were to measure the time it takes to transfer the heat, we'd find that the transfer doesn't occur instantly. It takes time. For example, if additional equipment is placed online, a change in cooling water temperature could occur. And it would be some time before a change would occur in the temperature of the raw water. The time it takes for the temperature change to be transferred from the cooling water to the raw water is a delay in the process. It's caused mostly by the resistance, capacitance, and dead time characteristics of the process. Resistance is a characteristic of a process that opposes the transfer of energy. In this case, the energy is in the form of heat. Capacitance is a characteristic of a process that enables it to store energy. Dead time is simply a period of time in which a change has occurred in the controlled variable, but the change has not yet been sensed. Let's look more closely at these characteristics. Here's an illustration of one of the heat exchanger tubes. Heat is transferred from cooling water inside the tubing to raw water outside the tubing. In effect, the heat has to go through the tubing. The tubing has material properties that oppose or resist the transfer of heat. These material properties cause the resistance that is present in the process. Of course, the resistance could be changed by constructing the heat exchanger's tubes of a different metal, perhaps a better conductor of heat. But some resistance would always be present. What you should know is that all processes will have some form of resistance that will affect the way the process reacts to a change in a variable. Now let's look at the heat exchanger again. This time we'll look for capacitance. Water has the ability to store heat. In the heat exchanger, most of the process capacitance is in the water. The amount of capacitance is related to the volume of water in the heat exchanger. And of course, the water volume is related to the size of the tubing and the water's flow rate. Since the tubing size is fixed, the capacitance that is due to the cooling water is maintained constant by keeping the cooling water flow rate constant. But the capacitance of the raw water is allowed to vary. For example, increasing the volume of raw water flowing through the heat exchanger with this actuator valve assembly increases its capacity to absorb heat. So in this system, the capacitance is carefully controlled. Other systems will have different resistance and capacitance characteristics, and you should be aware of them because they will affect the way the system responds to a change in a variable. When you tune a system, this is what you should be most concerned with: how the system responds to a change in a variable. The third major process characteristic that you should be aware of is dead time. Dead time in the heat exchanger process is the delay that occurs between the time the cooling water temperature changes and the time that the change is first sensed. It is directly related to the distance between the process and the sensing element. For example, if the sensing element is close to the process, there should be very little dead time. If the sensing element is further away from the process, there will be more dead time. The main problem with dead time in a control system is that the controller cannot initiate control action until after the change has been sensed. In some systems, this delay is critical. In others, it isn't. As you gain experience tuning control systems, you'll become more aware of dead time and its effects. Now that we know about resistance, capacitance, and dead time, let's see how these characteristics affect the response of our cooling water system. Let's begin by defining some of the system operating conditions. First, the flow rate and volume of the cooling water is held constant. Second, although the raw water flow is controlled by this actuator valve assembly, we'll assume that for now it is constant. And let's also assume that the temperature of the cooling water is 85 degrees Fahrenheit. And that the temperature of the raw water is 70 degrees Fahrenheit. We'll use this chart to compare the temperature of the cooling water with the temperature of the raw water. The vertical axis will be temperature in degrees Fahrenheit, and the horizontal axis will be time in minutes. Note that both temperatures are constant during the first 10 minutes. Now, what we want to know is how does the controlled variable, the cooling water temperature, react to a change in one of the other process variables? For the purpose of this discussion, let's assume that the temperature of the raw water has changed because the cooling tower has been temporarily shut down for maintenance. This part of the graph shows the resulting step change in raw water temperature. At 10 minutes, the temperature of the raw water changes from 70 to 75 degrees. Now remember, our question is, how will the resistance, capacitance, and dead time characteristics of the system affect the cooling water temperature after the raw water temperature changes? Now here's how the process responds. Notice that although the raw water temperature changes at 10 minutes, the cooling water temperature did not begin to change until about 12 minutes. This is the dead time in the system. Notice that initially the cooling water temperature change occurs quickly after the dead time has passed. But due to the amount of resistance and capacitance in the system, the total temperature change takes a much longer time. The total change in cooling water temperature lags the change in raw water temperature, in this case by about 10 minutes. This 10 minutes is called the lag time. In any system, the lag time will be the total time it takes the controlled variable to stabilize after a disturbance occurs. A disturbance is a change in process operating conditions that affects the controlled variable. Lag time is often called response time. The shape of a process reaction curve during its response time is determined by the process resistance, capacitance, and dead time characteristics. You can expect different types of control systems to produce different reaction curves. The reaction curves that we've seen up to now are for open-loop control systems where the controller is in manual or hand. A closed-loop system will produce a different reaction curve. That's because the controller will begin control action as soon as the measured variable begins to deviate from set point. This is the cooling water temperature reaction curve produced when the loop is open. The controller is in manual. And this is the reaction curve produced when the controller is in automatic and is properly tuned. It's a typical closed-loop reaction curve. These are called peaks, or overshoots. This dotted line represents set point. Here you can see that the cooling water temperature has increased until it has passed set point. This is the first overshoot. Here it decreases, then increases, until it again passes set point. This is the second overshoot. The height of these overshoots can be used as an indication of how good the control is. In general, you have good control when the ratio of the height of the second overshoot to the first overshoot is about 1/4. This relationship also applies to the following overshoots. The ratio is called the quarter decay ratio, and it's important because it indicates how quickly the system will recover after a change in the process variable. However, don't expect to see a quarter decay ratio in every system you tune. You may not see it in many systems. It's the ideal. So, process characteristics are reflected in process reaction curves. And reaction curves provide clues as to how a process might be tuned. Later, we'll see how the reaction curve is used during the tuning procedure. But first, review the material in your text. When we return, we'll look at a method of tuning control systems. When you tune a pneumatic control system, you should follow a logical procedure. So in this part of the program, we're going to look at a commonly used tuning method called the systematic trial method. There's a couple of other methods that you may sometimes use, the reaction curve method and the ultimate gain method. You'll find these two methods discussed in your text. Now, in the systematic trial tuning method, as well as with other methods, you must have the process up and operating before you begin. And you must always tune for stability. That is, after a disturbance, the system should return to a control point within a reasonable period of time. Here's the closed-loop reaction curve for a stable system. Notice that the process variable begins to change from set point here and settles out near set point here. This is the system's response time. The important point here is that you adjust the controller to vary the system response time. As you recall, response time is the time it takes the controlled variable to stabilize after a disturbance occurs. You vary response time by adjusting gain, reset, or rate, depending on which control modes the controller has. Now, both reset and rate adjustments will affect the gain of a controller, and it's the gain that can cause a system to become unstable. For example, this is the reaction of a system where the gain is just as high as it can be without making the system unstable. The length in time of this part of the curve is called a period. These are cycles. Each cycle is one time period. And as you can see, the process variable is continually cycling. Ordinarily, a stable system will show very little cycling. For example, on this curve, which shows a quarter decay ratio, there's very little cycling. But on this one, where the gain is much too high, the cycling is continuous, and the overshoots are getting larger and larger. This system is unstable. Remember, you are going to adjust the controller for minimum cycling, but at the same time, you'll adjust for gain, reset, and maybe rate to compensate for some of the characteristics of the system. In the end, what you get will be a compromise between what you want and what you can get the system to do. In general, when you use the systematic trial method, you'll follow just a few basic steps. After notifying operating room personnel, you begin tuning with the system operating normally and the controller in manual. If used, set the reset control to minimum. And of course, if there was a rate control being used, you'd also set it to minimum and turn the gain control to a minimum setting. Some controllers have a gain control while others have a proportional band control. As you know, proportional band, or PB, is the reciprocal of gain. If PB is high, gain is low. A PB of 100% is a gain of 1. We're going to use only the term gain in this unit, but you should be able to make gain or PB adjustments. Now, when you begin tuning, you start with low gain because the system is usually stable when the gain is low. It becomes less stable when the gain is increased. Next, you put the system in automatic and make a load change. A load change is simply varying something in the system that will cause the controlled variable to change. You can generate load changes several ways. You can manually operate a control valve to cause the controlled variable to deviate from set point. You can turn some equipment on or perhaps off. Or you can simply change set point. Usually a set point change of 5% or so is sufficient to simulate a load change. You'll change set point with your controller in automatic, but you always put the controller in manual to make gain, reset, or rate adjustments. Once you've generated or simulated a load change, you'll observe the process reaction curve to see what effect the low gain had on the system. Here's an illustration of a reaction curve when the gain is too low. This line represents the load with a step change here. When the step change occurs, the controlled variable changes. Notice that there is no cycling and that the controlled variable quickly stabilizes at a new value. This is not set point. It is a new control point. This dotted line is set point. The difference in the new control point and set point is called offset. Offset is a characteristic of a control system that has only gain or proportional control. To eliminate offset, you adjust the gain until you have about a quarter decay ratio. Then you increase reset until the offset is gone. To do this, you'll have to correctly interpret reaction curves. For example, this reaction curve shows less offset than the one we just saw, but it doesn't have a quarter decay ratio. There's very little cycling, but it still shows a wide offset. Now, if the gain were turned too high, the curve would look like this. This curve has very little offset, which is good. But it also has excessive cycling. It's cycling because the decay ratio is too high. It's taking too long for the system to stabilize. Now, if the gain were much higher, the system would cycle continuously. You don't want that. So you turn the gain back down a bit, and you get this. Here we see a quarter decay ratio and some offset. This curve represents a compromise. It's the best gain setting for the system. It has minimum cycling and minimum offset. If the gain were less, the offset would increase. On the other hand, if the gain were higher, the cycling would increase. So we have a compromise between stability and offset. If the controller you're tuning has a reset mode, the next thing you do, using the systematic trial method, is to adjust the reset. There's two very important things you have to know about reset. One, since reset repeats the amount of proportional output, increasing reset will act the same as increasing the gain. So as you increase the amount of reset action, you have to decrease the gain. Two, You will increase the reset until you get excessive cycling. Then you'll decrease it just enough to stop the cycling. In general, the procedure for adjusting reset is the same as for gain. Increase it, create a load change, then observe the reaction. Remember, the controller is in manual when you're adjusting it, and it's in automatic when you make load changes. These three reaction curves illustrate low, correct, and high reset settings. This curve shows that the offset is gone, but it's taking too much time for the controlled variable to stabilize. This curve shows too much cycling, even though it stabilizes in less time than it did with too little reset action. And this curve shows what you can expect to see if the reset is correct. The controlled variable stabilizes in minimum time. There's no offset, and there's very little cycling. So in general, you'd begin with a minimum amount of reset and expect to get this reaction. Then you'd increase reset until you get this reaction. And finally, you decrease reset a bit until you see this reaction. After adjusting reset, you'd adjust the rate control. Now, rate action, as you recall, will increase the speed at which control action is applied. It also affects gain, so you'll have to decrease the gain whenever you increase rate. Here's an illustration of the effects of rate action in a control system that has proportional and rate control modes. This shows that the rate action is set correctly. The controlled variable stabilizes quickly with little cycling. The curve shows offset because there's no reset action in this system, just gain and rate. This is what happens when the rate is set too low. There's some cycling, and it takes longer to stabilize. And this is what you'll see whenever rate is set too high. There's obviously excessive cycling. This completes our discussion of the systematic trial method of tuning. You should remember that when you use this method, you adjust the gain or proportional band first, then reset, and finally rate. Always begin with low settings and slowly increase them until you find the setting that is most correct for the system you're tuning. And of course, whenever you increase reset or rate, you should decrease the gain. Now review the material in your text on tuning methods. If you have any questions, ask your instructor to assist you. In this part of the program, we're going to see how a pneumatic control system was tuned. Before we do that, though, we need to take a closer look at the system, our cooling water temperature control system. During tuning, the temperature of the raw water was kept constant. In other words, the technician ensured that no one shut down the cooling tower or added water to the system from the river. The idea was to make sure that nothing changed during tuning except the cooling water temperature. Raw water flow changed depending on the signals that were sent to the actuator valve assembly. On the other hand, the flow of cooling water remained constant, while the temperature of the cooling water, the controlled variable, changed. The cooling water temperature ranged from about 65 to 105 degrees Fahrenheit. Set point in the system is 85 degrees. When the technician changed set point to create load changes, the cooling water temperature did not vary more than 10 to 20 degrees above or below set point. As a safety feature, an alarm sounds in the control room whenever the cooling water temperature reaches 115 degrees. The system's controller is a typical PI controller. Its gain is normally set to 1. This is a proportional band of 100%. And the reset control is normally set at 1 repeat per minute. This means that the controller repeats the amount of proportional output each minute the cooling water temperature is away from the set point of 85 degrees. The system control loop operates on a pneumatic pressure range of 3 to 15 psi. When tuning this system, the technician had to relate to both temperature indications and percentages. This is because most of the instruments in this system indicate percentages of the temperature range rather than actual temperatures. For example, the cooling water temperature transmitter's output is in degrees Fahrenheit, while the hand station gauges indicate temperature in percentages of 0 to 100%. The recorder also indicates temperature as a percentage of 0 to 100%. So when tuning, the technician had to know the relationship between temperature in degrees Fahrenheit and percentage of temperature range. This is how the technician had to think about the indications. Since the temperature range is 200 degrees and the percentage range is 100%, then 200 degrees is the same as 100%. And 2 degrees is the same as 1%. Or 1/2 of any temperature indication is its equivalent percentage. Since set point is 85 degrees, and 1/2 times 85 is 42.5, set point equals 42.5%. And since 1/2 of the alarm temperature is 57.5 degrees, the alarm sounds at 57.5%. This also means that when the technician is reading percentages at the hand station or the recorder, all he has to do is double the percentage to get temperature. For example, 40% is 80 degrees, 45% is 90 degrees, and so on. Keep in mind that this relationship is good only for the cooling water system. There will probably be different relationships for the temperature control systems in your plant. Here's the hand station that's used in the cooling water system. The A gauge indicates cooling water temperature. The B gauge indicates set point. The C gauge shows the transfer signal, and the D gauge indicates the output of the controller. This is the selector knob. It's used to select manual or automatic control. This control adjusts set point in the system. And this control adjusts the transfer signal when the hand station is in automatic. It also adjusts the controller's output when the hand station is in manual, which means it's controlled by hand. Knowing how to use this control is important. For example, before the hand station is switched to manual, the control is adjusted until the transfer signal matches the controller output signal. Then, when the hand station is switched to manual, the controller's output won't change. If the transfer signal is not matched with the controller's output before the switch, the controller's output will change when the selector is switched. The change will cause the final control element to momentarily move. This will appear as an undesired bump in the reaction curve. When the transfer signal is properly matched with the controller output signal, the bump will not occur. This is known as a bumpless transfer. Making bumpless transfers saves time by eliminating undesired changes in the process. Technicians don't tune control systems just because they feel like it. There's usually a good reason. In the case of the cooling water temperature control system, the control valve was replaced with a different valve. The new control valve was expected to respond more slowly than the old one, so engineering gave the technician new controller settings to use. As you recall, with the old valve, the controller was set for a gain of 1, and a reset of 1 repeat per minute. The technician was told that with the new valve, the controller should be set for a gain of 1.9 because the new valve had a slower response. So the system would need faster control action. Then, because a higher gain typically results in less offset, the new reset value did not have to be as much as it was for the old valve. The new value was calculated to be 0.2 resets per minute. Let's see how the technician prepared to tune the system. First, he discussed the system with both operating and engineering personnel. Then he studied the P&IDs, control logic diagrams, the appropriate service manuals, and the calibration records. After studying the system and talking to the right people, he had learned what he needed to know to tune it. For example, the system response time with the old control valve was 15 minutes. The engineer assured him that the new controller settings should keep the response time at about 15 minutes. The technician also learned how much he could vary the cooling water temperature and still keep the process within its safe operating limits. This chart can be used to illustrate what he learned. The chart's vertical axis is the temperature of the cooling water in percentage. The horizontal axis is time. The critical temperature is at 57.5%, or 115 degrees. The alarm will sound if the cooling water temperature gets this high. Set point is 42.5%, or 85 degrees. This information told the technician that he could vary cooling water temperature by as much as 15%, or 30 degrees, before the alarm sounded. In studying this information and in talking with the engineer, the technician learned that he could change set point by about 5% and still keep the cooling water temperature within that 30 degrees between set point and the alarm temperature. Of course, he wasn't concerned about causing the cooling water temperature to go too low. There was no danger in that. Now, whenever you tune a system, if there's no critical point below set point, always make sure your first change is down from set point. The second change, of course, can be up toward the original set point. So, after studying the system and deciding basically how he was going to tune it, the technician was ready to begin. He decided that he would remove the controller, take it to his shop, and calibrate it using the new settings. This is a standard procedure. After putting the controller back in the system, he planned to change set point 5% downward and see how the system responded. If the system stabilized at the new control point in about 15 minutes with minimum cycling, it would be tuned. If not, well, we'll see about that in the next part of the program. But before we do, take the time to read over the material in your text. Ask your instructor about anything you don't understand. As you recall, when we ended the last part of the program, the technician had made all the necessary preparations for tuning the system. He studied the system thoroughly. He talked with operators, engineers, and other technicians about the system. He became familiar with the system's characteristics. He knew how it should respond to load changes. He was aware of its operating characteristics and its limitations. And finally, he asked a control room operator to stand by while the system was being tuned. Now, in your plant, the operator may have to make all hand station adjustments. But in this plant, as in many others, the technician makes the adjustments while an operator remains nearby in case he's needed. After calibrating the controller, the technician reinstalled it in the system. Once the controller was in the system, he informed the operator that he was ready to begin tuning. Before he began tuning, though, he made sure that the cooling water temperature was at set point, 42.5%, and that the transfer signal matched the controller's output. Since they matched, he switched the system from manual to automatic. Here's an illustration of what the reaction curve looked like when the system was switched to automatic. These numbers indicate percentages, and each horizontal line is equal to 2%. These vertical lines represent time, and each line is usually equal to 15 minutes. But in this illustration, the lines have no value. This is the sort of thing you'll see when you change the chart speed on the recorder so you can see the reaction curve more easily. It's something that's done quite often during tuning. This line at 42.5% is the cooling water temperature. It's right at set point. During this time, the system was in manual and there were no load changes. Right about here is where the hand station was shifted to automatic. Since the line did not move away from set point, it was a bumpless transfer and the system remained stable. Once the system was in automatic and was stable, the technician adjusted set point down by 5%. From 42.5% to 37.5%. This simulated a 5% load change. After about 20 minutes, the technician went to the recorder to see how the system responded to the load change. Here's an illustration of what he saw. The cooling water temperature has stopped cycling at 36%. There was an offset of about 1.5%. Now, in your plant, an offset of 1.5% after this length of time may not be a problem. But for the purposes of this discussion, it is a problem and will have to be adjusted. Another thing that the technician noticed was that there appeared to be excessive cycling and that it took a little too long to stabilize. The curve's decay ratio is the ratio of this peak to this peak. This peak was about 2.5% below the point where the cycling stopped, 36%. And this one was about 6% below it. So the decay ratio was about 0.4. Which was too high. The technician knew that something around 0.25 or 1/4 is what it should have been. So the curve indicated cycling, excessive response time, and a small offset. All of these things pointed to the gain being too high. Now, once the technician knew this, he realized that the engineer's settings were a little off, so he decided to tune the system from scratch. After deciding what to do, the technician adjusted the hand station for a bumpless transfer, switched the control system back to manual, and adjusted the cooling water temperature back to the correct control point of 37.5%. At that point, the technician knew that the new gain of 1.9 was too high for the system, so he decided to try the old gain setting of 1. He knew that the correct gain would not be any lower than the old gain. This was also consistent with the systematic trial method. Begin with low settings. So he tuned out the reset by turning it to its most minimum value and adjusted the gain to 1. After placing the system back into automatic, adjusting set point from 37.5% to 42.5%, and waiting for the system to stabilize, he analyzed the reaction curve. This is an illustration of what the technician saw. It indicates a low gain problem. There was almost no cycling. The temperature stabilized very, very quickly, and there was a 3.5% offset. This time, the temperature stabilized at 46% when it should have been 42.5%. In this system, this is a wide offset, and it indicates that the gain is too low. So the technician placed the system back in manual, adjusted the gain up a bit to 1.3, and after returning the system to automatic, he changed set point from 42.5% to 37.5%. Here's an illustration of the reaction curve he got this time. The new control point was 35%, so the offset was 2.5%. There was little cycling, and the decay ratio was still obviously less than 1/4, so he decided the gain was still too low. The third time he adjusted the gain, he set it at 1.6. This meant that it was almost where the engineer had said it should be. He expected it to be either very close or right where it should be. And it was. Here's an illustration of what he saw when he had the gain adjusted correctly. A characteristic quarter decay ratio curve with a small offset. Set point was at 42.5%. The new control point was 44.5%, producing an offset of 2%. The ratio of the height of this peak to this one was just about 1/4. Except for the 2% offset, the technician had obtained just about the ideal curve. He could have decreased the offset by increasing gain, but he knew that that would also cause excessive cycling. So, he had the best gain setting for the existing process conditions, but that's not the gain setting he entered into the calibration record. He knew that he would have to tune in some reset action to get rid of the offset. He also knew that the reset would act to increase gain, so the gain of 1.6 would have to be changed, and the final correct setting would depend on how much reset action was required. Before we see how the technician determined the required gain and reset settings, read over the material in your text. Ask your instructor to explain anything that you don't understand. In the last part of this program, we saw the technician use the systematic trial method to adjust gain in the cooling water temperature control system. You'll recall that he had found the best setting for the gain control, and he had decided to tune the controller for reset action. In this part of the program, we'll see how the technician tuned for reset action. This illustration shows the type of response he was looking for. Set point is 37.5%. After a load change, the cooling water temperature would stabilize at set point. There would be no offset, almost no cycling, and the temperature would easily stabilize within the expected time of 15 minutes. Now let's see how the technician tuned for reset action. He began by switching the system to manual and went to the controller to adjust reset to 0.2 repeats per minute. 0.2, as you recall, is the setting that was suggested by the engineer and was considerably lower than the old setting of 1 repeat per minute. The engineer's suggested setting was pretty low because the new gain setting was expected to be about twice as high as the old one. Higher gain results in less offset, so the system shouldn't have needed as much reset action. Now, you tune for reset action because you want the controller's output to continuously increase as long as the controlled variable is away from set point. You don't want to increase the gain in the system. So whenever you increase reset, you should always decrease gain. There's a way to calculate the exact amount of gain required. It's discussed in your text. So, the technician performed the necessary calculations and determined that a reset of 0.2 repeats per minute required that he decrease the gain setting from 1.6 to about 1.3. He returned to the hand station after setting the controller's gain and reset controls. There, he placed the system in automatic and made a 5% change in set point. Here's an illustration of how the system responded. There was no offset. The cooling water temperature stabilized at set point 37.5%. There was some cycling. Not much, though. But it took too long for the temperature to stabilize. This told the technician that the reset was working, but there wasn't enough of it. Even a small amount of reset will cause a controlled variable to eventually return to set point. But what the technician wanted, and what you will want when you tune a system, is to get the controlled variable back to set point quickly, with minimum cycling, of course. So it was back to the controller again. This time, the technician decided to try a reset setting of 0.8. He'd learned that 0.2 was way too low. He knew that 1 was probably too high, so he figured 0.8 might be close. After setting the reset to 0.8 and decreasing the gain to a point he had determined to be correct, he observed the process's reaction. Here's an illustration of what he saw. The reset was too high. The temperature had quickly returned to the set point of 42.5%, but it had overshot it and cycled. Of course, the cycling had caused it to take too long to stabilize.